Now for the second video of kinematic motion, we are looking at angular motion this time. So the same concepts are being discussed, distance and displacement, speed and velocity. The only difference being this time we're talking about the angular versions of those things. So we're looking at rotational motion. So here are some examples of angular motion. The hammer throw, before the person spins with the hammer throw, is undertaking angular motion, or the ice skater is undertaking angular motion around an internal axis of herself. So the axis, like you can see in this image, is simply the center point in which a rotation is occurring around. All right, so you can see this tire is rotating clockwise around this axis being the center of the wheel. Okay, so the fixed point in which a rotation occurs around is known as the axis. This can be imaginary, like someone doing a tumble turn. There's no actual bar that they're tumble turning around. There's an imaginary axis in the middle. Or it can be a real axis like you can see with this wheel, like a bar in which a gymnast rotates around. So here's some more examples of angular motion, but firstly, a definition is the rotation of a body or body parts around a central or fixed axis. So it can be described using the same terms as linear motion. So we're talking distance, displacement. We just call it angular distance, angular displacement, angular speed, angular velocity. Okay, so that just helps us distinguish that we're talking about rotational movements. They're measured in degrees because they are rotating around an axis. So 360 degrees is one rotation. All right, but we can see some imaginary axis of the diver, a real external axis, and imaginary internal axis in the center of the ballerina. Okay, so there's no actual pole that she is rotating around. It's just the center of her is the axis that she is spinning around. Right, so many linear body movements result from angular motion of body parts. So even though you're moving linear direction like this cyclist or this runner, they're both moving in rectilinear motion going forward as a whole. But if you look at the runner's legs, they are rotating around the pedal or causing the wheel to rotate around, propelling the bike in a rectilinear motion. So you can see there is rotation happening in the legs of the cyclist in order to propel that bike forward. Same with the runner. There's rotation of the leg to complete that motion in order to generate power and move rectilinear motion. So you can pause this video right now and give this a try yourself. See if you can spin around on a swivel chair if you have one in the house. And can you make yourself speed up without applying any more force? And can you slow yourself down without applying any more force? So, looking into the more specifics, angular distance and angular displacement. Now, if you remember from linear distance and displacement, distance is the total distance that someone moves, walks, runs, okay, and displacement was simply the starting point to the ending point in the quickest way possible. So it's very similar with angular distance and displacement is the total of all angles that change the result of an object or body part between the starting point and the ending point, or the starting and the finishing point. So between B and C, that angular distance is the degrees in which that person has moved between those 2 points. Okay, if we're looking at angular displacement, so let's say this person started at A and they finished at D. The angular displacement is 180 degrees. Their distance is 180 degrees. So let's look at this in a little bit more detail. A gymnast starts their angular motion upside down on a high bar in point A, which, as you can see, that person upside down there at 0 degrees. They then complete 1.5 rotations, so once around and another half, and land upright. Okay. In point D, calculate the gymnast's angular distance and angular displacement. So, angular distance, if one rotation is 360 degrees, we're saying that they did 1.5 rotation, so a half of a rotation is 180 degrees. So, simply plus those two numbers together, and we get an angular distance of 540 degrees. Displacement, we're going to get a different figure because it doesn't take into account the whole distance, the starting point to the ending point. So it might have been 540 degrees. Point A was 0, point B was 180. Nothing else matters except the starting and the ending point, so A and B in this case. As a result, that angular displacement is 180 degrees. So here's another good example where you can see the difference. The bowling ball started in this guy's hand back here. He's bowled it this whole way through. The distance that the ball moved through his arm was 240 degrees. The displacement, even though the ball didn't move this way, is the shortest way from point A to point B. So in this case, 120 degrees. Okay, so displacement of the ball was 120 degrees, even though the ball didn't travel that way. It's simply the quickest way. So, another little practice question here. What is the displacement of a ballerina who performs a stationary double pirouette with an angle to the distance of 540? So, remember, one spin is 360, another spin, another half spin makes 540. So, they've done 1.5 spins. So, their distance would be 540. However, that's not what the question is asking. It's asking for a displacement. And in this case, the displacement would be C, 180 degrees. So now we're looking at angular speed and angular velocity. And this refers to the angular distance covered divided by the time taken. So similar to speed in linear motion. Okay, for an example, a rotating object that completes 2 full revolutions per second would have an angular speed of 720 degrees. All right, and we get that because they've done 1 second, and in 1 second they've done 2 rotations, so that's 360 times 2. All right, and the time is 1, so 720 degrees per second would be the angular speed of that. Okay, if we're looking at angular velocity, the same as before. All right, it takes into account the displacement velocity. Okay, so it's the initial angle and the final angle divided by the time taken. So it's measured by dividing the angular displacement by the time taken. So it should specify the direction of the rotation as well. So let's have a look at some examples. All right, just to compare the two together. The distance divided by the time, or the displacement divided by the time. Both are measured in degrees per second. The angular velocity will also include the direction in which it's moved, so clockwise or anti-clockwise. Okay, why is this important in sport? Speed of rotation is important for athletes who have to perform twists and spins, such as diving, gymnastics, ice skating, dancing. In order to complete more twists or spins, they need to have a higher angular speed. Okay, so increasing the angular velocity of body segments in a throwing action results in a higher release. Okay, so if I can propel my angular velocity of my arm as a cricket bowler, that is going to greatly increase the ball speed at which I release out of my hand at the end of that rotation. So, angular velocity required, I've already mentioned this one, but just to give you an idea of just how fast their angular velocity can get, studies have shown that ice skaters performing a triple axel, which is 3.5 rotations, at their peak velocity, it's over 1,800 degrees per second, incredibly quick. So, increasing the angular velocity. I was just started to explain this about a cricketer. All right, you can see the velocity of that arm coming through. That velocity is going to be transferred to that ball. So obviously, it's very beneficial for a fast bowler to have high velocity in their angular velocity of their arm in order to transfer that into a high velocity of the ball when it's released. So, how would you calculate angular velocity? Quite simply, the angular velocity is the angular displacement of an object within a given time frame. So it can be calculated by the angular velocity equals angular displacement divided by time. So to get the angular displacement, it would be the starting angle and the ending angle. So there's one other concept that you need to be aware of, and it's a little difficult to get your head around at first. All right, it's this golf club here and the idea of radius of rotation. So the radius being from a center point and to the end point. So the radius of A would be from this green circle to this first black dot above A. Right, so quite a small radius. And whereas B would be from this green dot all the way to B here. So it has quite a larger radius. And basically the relationship is the larger the radius of rotation, the larger the angular velocity. Why is that, you might ask? All right, because point A has a small radius of rotation, point B has a large radius of rotation, but both of them get to where they need to go at the same time. So which one's covering more distance here? A is going from here to here, so quite a small angular distance, whereas B is going all the way around here, and they're doing this in the same time frame. So basically, the end of the club has a much higher angular velocity than the beginning of the club because it's got a much higher distance that it's traveling. So let's put this in a question. Angular velocity can be increased by increasing the radius of rotation. Rank the following sporting implements in order from the most likely to increase linear velocity of an object being struck to least likely. Now remember, the length of the radius is what determines. So think about where the person is holding the piece of equipment and where the radius of rotation is from where they're holding until the release point of the object. So, quite simply to answer this question, the largest object is going to have the biggest radius of rotation, and therefore it's going to increase the linear velocity the most. So, the number one rank would be the lacrosse stick because it's 183 centimeters. Number two, 137, the polo mallet. We have the golf driver, and we have the baseball bat, and we have the hockey stick. Okay, so it's just been ranked from the longest radius of rotation to the shortest. There's other factors at play, but that question is specifically asking about just that factor, so that's all you need to think about. So, what is the difference between angular distance and displacement? Angular distance is the total amount of degrees covered from the start of an angular movement to the end point, following it the whole way. All of them added up. Okay, the angular difference in degrees, so that's the angular displacement, that should say, is the difference in degrees between the starting point and the ending point of a movement. Angular speed is the angular distance covered within a certain time frame, and it's calculated by angular speed equals angular distance divided by time taken, whereas angular speed is measured in degrees per second. Angular velocity is simply the initial angle minus the final angle divided by the time taken. So that should be specific about the direction. For example, 180 degrees clockwise. All right, so now you can pause this, have a look at this and compare the two. If you didn't know what a skeleton bob is for the sporting examples, right, it's these crazy guys here who linear motion straight down the center of the bobsled arena. Right, and there's the difference, okay, between the forces applied how it creates rotation as opposed to linear motion. So, can you please complete these questions and let me know if you have any issues?